Section 5.6 is about phase shift and sinusoidal curve fitting. For this part, you are going to need a graphing calculator. So for the graph y equals a sine of omega x minus phi, this is phi, or y equals a cosine omega x minus phi, as long as omega is greater than 0. We know how to calculate the amplitude and period. We learned that in section 5.4 and 5.5. But now we're adding something else, which is phase shift, which is phi over omega. The phase shift to the left is to the left, right, if phi is less than 0, and to the right if phi is greater than 0. That's just the same thing we did before for left and right horizontal shifts, right? The phase shift, okay, is how far the function is shifted from its usual position. So here we've got a phase shift, right, of pi over 2, right? It's shifted pi over 2 from its normal position. So first, let's find the amplitude, period, and phase shift of a sinusoidal function, and then what we're going to do is we're going to graph it. So I have y equals 3, that's our a, sine of 2x minus pi. So that means 2 is our omega, and pi is our phi. So our amplitude is the absolute value of 3, which is 3. Our period is t equals 2 pi over our omega, which is 2. So our period is pi, right? That means our function repeats itself every pi. And our phase shift is phi over omega, which is pi over 2. So our graph is going to be shifted pi over 2 to the right, because it's subtraction, to the right from our standard graph of a sine function. So let's practice graphing this in 4 steps. So the first thing I need to remember is that my phase shift is pi over 2, and my period is pi. So let's graph. First, we're going to graph sine of x. Then we'll graph 3 sine of x. Then on the next slide, we're going to graph 3 sine 2 of x, and then we're going to shift it by minus pi. Remember that 2 of x, that's our horizontal compression by 1/2. Okay, so sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, sine of 2 pi is 0. Do you have to memorize these? No. Is it good to know them and to feel really confident with your unit circle? Yes. Next, what we're going to do is we're going to multiply this function's outputs by 3. Its outputs are its y. This was 1. Now I've got 1, 2, 3. So 0 stays 0. Pi over 2, which is 1, becomes 3. 0 stays 0. 3 pi over 2, which is -1, becomes -3. And pi over 2 becomes 0. So this is my new function. Next, on the next slide, we're going to do our horizontal compression. That's going to change our period from that of the standard sine function, right? It normally has a period of 2 pi. Now we're going to be smushing our period by 1/2. So now I have y equals 3 sine of 2 over of 2x. So 1, 2, 3, 1, 2, 3. So instead of everything happening over a period of 2 pi, now we're squished down to a period of pi over 2. So we're 2 pi, sine of 2 pi before was 0, now sine of 1/2 is 0. Let's mark some other points. Sine of pi over 4 is going to become 3. Pi over 2, whereas before pi was 0, now pi over 2 is 0. Whereas before 3 pi over 2 was -3, now we're going to have it be 3 pi over 4, because it's that horizontal compression by 1/2. So you're multiplying your x values by 1/2. So we go ahead and shift this, doop, 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 doop. And remember that our graph repeats itself because it's a periodic function. Okay, here's our new graph. Y equals 3 sine of 2x. Last but not least, we're going to phase shift our graph, not by pi. Remember, it's phi over omega, which is pi over 2. And we're going to shift it to the right. So let's mark this. So basically, I am moving everything pi over 2, right? So this point, 0, is going to move to pi over 2. This point, pi over 4, is going to move to 3 pi over 4, right? So everything is shifted by pi. This is going to move here. This is going to move here. Wait, I didn't do that right. This is going to move here, right? So we can see that my graph is shifted by pi over 2. Let's graph it more neatly. So I'm going to have what was 0 is now pi over 2 and pi, right? Because we squished it. And then we shift it by pi over 2. So we pushed it to the right, pi over 2. So now my positive 1's up here, negative, 3. Okay, so this is my new function, remembering that it does repeat itself. So now we have graphed it beautifully using function transformations. Now, what if I didn't want to graph our function y equals 3 sine of 2x minus pi using function transformations? I could do so by finding 5 points on our function and graphing those. So remember, our amplitude is 3, our period is pi, and our phase shift was pi over 2. In order to determine our 5 key points, we're going to look at the interval from our phase shift, because we know our graph's been shifted from 0, it's been shifted by pi over 2, and we want to go to pi over 2, that's the shift, plus our period. So we're going to be looking on the interval pi over 2, 3 pi over 2. And I know that the distance between these 2 points is pi. So if I break this up into 4 subintervals, right, I'm going to be taking pi divided by 4, which is, of course, pi over 4. And I want to add that to find each of my 5 x coordinates. So our first x coordinate is going to be pi over 2. Then I'm going to add pi over 4 to that, and I get 3 pi over 4. And that'll be my second. Then I'm going to take 3 pi over 4 and add pi over 4. That would give me that just gives me pi. And that's our third x coordinate. Then I'm going to take pi plus pi over 4, again, because our interval was pi, and I want to find 5 points in order to graph our sinusoidal function. This gives me 5 pi over 4. This is our fourth coordinate. And our last coordinate, if I take 5 pi over 4 and add pi over 4 to it, I get back to 3 pi over 2. That's our fifth. So these are the x values we are going to want to plug into our function. So have your unit circle. That was the sound of me getting my unit circle. Have your unit circle handy. So if I have y equals 3 sine of 2 times pi over 2 minus pi, well, that's y equals 3 sine of pi minus pi. Y is 3 sine of 0. Well, sine of 0 is 0, so our coordinate, our y value is 0. So now we have the coordinate when x is pi over 2, y is 0. For our second, I'm going to take y equals 3 sine of 2 times 3 pi over 4 minus pi. That's y equals 3 sine of 3 pi over 2 minus pi, which is y equals 3 sine of pi over 2, which is going to give us 3. So now I have when x is 3 pi over 4, y is 3. And if you look back at the function we did graph, these points are on that graph. And you're just going to continue substituting for all of the additional values of pi. For y equals 3 sine of 2 pi minus pi, you get y equals 3 sine of pi, which is 3 times 0, so y is 0. So you have the point when y is when x is pi, y is 0. If I take y equals 3 sine of 2 5 pi over 4 minus pi, that's going to end up giving y equals 3 sine of 3 pi over 2, which would give us negative 1. So I have the point when x is 5 pi over 4, y is negative 1, and we'll do the same thing for 3 pi over 2 with what little room I have. Y equals sine, 3 sine, 2, 3 pi over 2 minus pi. It gets a little tiny, I'm sorry. But you're going to get y equals 0 for your final answer. So that's how you can also graph a sinusoidal function, by finding points instead of doing the graph transformations. But I do think it's really important for you to be able to visualize the graph transformations. So here are the steps for graphing sinusoidal functions, right? We find our amplitude, period, and phase shift. This is if you don't want to do it by doing the graphing. You define your interval between your phase shift and your phase shift plus your period. You break that up into 4 subintervals, and you use those endpoints to be the 5 key points. So your x values of your graph, and then you plot those points. And remember that if b doesn't equal 0, right? This is a vertical shift. If it's positive, it moves up. If it's negative, it moves down.